Hey guys, this is Professor Janacek. I want to go over some examples where we find equations of planes. So let's get started. Example 1, let's find the equation of a plane through the point 1, 0, negative 3 with the normal vector 1, negative 1, 2. So to start with, I'm going to go ahead and kind of identify the point. I'll call this x naught, y naught, and z naught. And also with the normal vector, I'll name this A, B, and C. And then we're ready to go. We have our formula kind of at the top of the page. It is A times x minus x naught plus B times y minus y naught plus C times z minus z naught is equal to 0. So in this case, we have 1 times x minus 1 times y minus 0 plus 2 times x minus negative 3 is equal to 0. So that gives us x minus 1 minus y plus 2z plus 6 is equal to 0, which is x minus y plus 2z is equal to negative 5. And there you go. Equation of the plane. Not so bad. Let's try another. Example 2, find the equation of the plane through, here we have 3 points. Point P is negative 1, 1, 1, and Q is 0, 0, 2, and R is 3, negative 1, negative 1. All right, so to start with, again, I will label P as my starting point, x naught, y naught, z naught, but I don't have the normal vector. We're going to have to find that. Well, first off, I would need to figure out the two vectors going from P to Q and from P to R. Again, that's why I needed to identify a starting point. Well, from P to Q, let's see that. Remember how to find this. It's 0 minus negative 1, 0 minus 1, and 2 minus 1 gives us the vector 1, negative 1, 1. All right, not so bad. From P to R, it would be 3 minus negative 1 minus 1, and negative 2 minus 1. Which gives us 4, negative 2, negative 3. All right, so there are the two vectors. Now I need the normal vector. I need it to be normal to this. Well, the normal vector here is simply going to be PQ crossed with PR. So remember how to find the cross product, determinant of the matrix. And take your time with this. Take a moment if you need. Figure out how to do this. Make sure you remember how to find the cross product. Let's see, and I think we end up with, it'd be 5. 7, and positive 2. Again, take your time with that. All right, well, that's not so bad. Now we'll use this as A, B, and C. So we end up with 5 times x minus negative 1 plus 7 times y minus 1 plus 2 times z minus 1 is equal to 0. We can simplify this just a bit. And we end up with 5x plus 7y plus 2z is equal to looks like a positive 4. And there you go. There's the equation of the plane. All right, on to example 3. Let's determine whether the planes are parallel, orthogonal, or neither. All right, in the first part of this, we have 2x plus 2y minus 3z is equal to 10. So this tells me that my normal vector is 2, 2, negative 3. I'll call that n1. The normal vector for the second one, n2, is negative 10, negative 10, 15. All right, so I just picked out the normal vector from each of those equations, so kind of going backwards on this part. But now looking at these two, I notice something. I notice that n2, again, that's negative 10, negative 10, negative 15. That's equal to, isn't that what, negative 5 times n1? Does that work? Ah, look at that, it does. All right, so one is a scalar multiple of the other. This tells us that n1 and n2 are parallel. All right, that's it for the first part. Not so bad. Okay, let's take a look at the second part. Again, let's go ahead and write out our normal vectors. The first one I'll call n1. The normal vector is 3, 2, 2. And the second one has the normal vector negative 6, negative 10, 19. Now, this doesn't look like they are scalar multiples of each other, so I'm guessing they're not parallel, but maybe they are orthogonal. Let's see, how do we determine if two vectors are orthogonal? Oh, we could use the dot product. So let's take a look at the dot product. Remember how to find the dot product. It's a little bit easier than the cross product. Not that either one of them is too terribly difficult, but let's see. To find the dot product, I will take the sum of the products of each component. Let's see, that's 3 times negative 6 plus 2 times negative 10 plus 2 times 19. Oh, let's see, what do we get? 3 times negative 6, negative 18 plus negative 20 plus 38. Oh, looky there. That gives us 0. Remember, this is a scalar, not a vector. But it gives us 0. The dot product was 0. That's exactly what we wanted. And that tells us n1 and n2 are orthogonal. And there you go. Enjoy.